Hello everyone, my name is Surush Kodrati and today I will present our work Planaria, which is about dynamic architecture fission for spatial multi-tenant acceleration of deep neural networks. With the ever-increasing demands for AI-based services, it has been projected that the total market for both cloud and edge solutions will increase significantly in the next few years. Moreover, due to the diminishing benefits from general-purpose processors, ASIC accelerators are becoming more prominent and it is being anticipated that they will take up around 40% and 70% for cloud and edge AI infrastructure market by 2025. As such, there is a heated arms race among leading companies for a speed of AI accelerators to dominate this large market. Now we are at this inflection point where the community is shifting towards specialized accelerators while demand for AI services are soaring. To cope with this transition, one straightforward approach would be constantly scaling out resources. However, low resource utilization in cloud data centers show that significant amount of resources are being wasted. To mitigate this serious underutilization, supporting multi-tenancy where a single substrate is shared among multiple tenants is inevitable. However, it has not been the primary factor in designing DNN accelerators up to now due to the arms race for building the fastest DNN engine. As accelerators are increasingly becoming ubiquitous, research on multi-tenancy of accelerators is imperative. To this end, multi-tenancy enables this leap towards deployment of programmable accelerators in a cost-effective manner. Now let's look at the history behind utilizing a specialized computing system and the role that multi-tenancy plays here. GPUs as one of the most powerful acceleration fabrics came out in 1999, and it was around 2001 that the first generation of GPUs emerged. Due to the vast adoption of GPUs in the computing fabrics, supporting multi-tenancy in GPUs became the next challenge to enhance the resource utilization, and it was 2009 that the first practical GPU with support for multi-tenancy through temporal task co-location emerged. In 2012, the case for a spatial task co-location in GPUs being motivated, and after that there has been more than 150 papers that have explored multi-tenancy in GPUs. With the huge advancement in AI algorithms and the slowdown of the trends in transistor scaling, community started a shift towards developing specialized accelerators for the domain of machine learning in 2014. Since then, more than 800 papers have been published about designing machine learning accelerators. However, the actual resource utilization in accelerators and their cost-effective adoption have not been the primary focus. Only in 2020, the community has started looking into this matter, and there have been two research works, namely PREMA and AIMT, that focus on multi-tenancy in DNN accelerators through temporal task co-location. However, temporal multi-tenancy does not fully tackle the issue of resource underutilization, as only one task is dispatched to the accelerator at any time. This paper sets out to explore a new dimension of spatial multi-tenant acceleration in DNN accelerators to promote utilization and enable that through introducing the new concept of dynamic architecture fission. We propose Planaria, an accelerator with architecture fission that enables the underlying hardware to dynamically break into multiple smaller logical, yet full-fledged DNN accelerators. This new capability by the hardware enables a spatial co-location of multiple DNN tasks and executing them simultaneously. To that end, bringing forth spatial multi-tenancy requires devising two main components. One, a microarchitecture with dynamic architecture fission capability, and a task scheduler that adaptively allocates resources to the dispatch task. To design the microarchitecture for fission, we consider a set of objectives. First, we need to design a microarchitecture that is capable of creating standalone full-fledged logical accelerators. Second, we need to enrich the fission possibilities and accelerator reconfiguration schemes to serve various computational demands of DNNs. Finally, the P-array and on-chip buffer bandwidth utilization needs to be maximized. While considering these objectives, there are also two design constraints that need to be taken into account. First, architecture fission should impose minimal power and area overhead to the hardware, and second, the baseline frequency should not be reduced. We enable architecture fission for TPU-style systolic accelerators in this work. But let's recap the systolic architectures. In a conventional monolithic systolic array, there is a 2D array of processing elements coupled with a unified multi-bank activation buffer for input storage, a multi-bank output buffer, and a 2D bank buffer for storage of the weight parameters. In this organization, the input activations flow horizontally from left to right, and the partial sums move vertically from top to bottom. As such, there is a waterfall-like unidirectional flow of data in regular monolithic systolic arrays. To realize fission for the 2D area of compute resources in systolic architectures, we need to provide a flexible mechanism to break the monolithic P array to multiple smaller subarrays. With flexible fission, an opportunity also arises to provide fission configurations suitable for different layers of DNNs that exhibit variegated degree of parallelism and data reuse for more efficient execution of DNNs. The left side of this slide shows a couple of them. However, fission needs to also happen at a fine granularity to amortize its cost. We perform a design space exploration for various options in the granularity of the fission to find the optimal and sweet spot. Another opportunity that arises is to reorganize the P subarrays in figure A and B and put them together to construct short and fat and tall and thin logical systolic arrays. These configurations could be very useful for DNN layers with high input activation reuse or high partial sum reuse. But enabling these new configurations require a new flow of data for the systolic array, which is omnidirectional data movement. As such, we propose omnidirectional systolic arrays that can forward the data in all directions in a cost-effective manner with minor additional logic to enrich the fission possibilities while minimizing the cost of long wiring, which may lead to curtailment of the clock frequency. In addition to the need for flexible fission in compute, the on-chip memory fission needs to also happen in a flexible pattern and should be balanced with the configuration of the subarrays. Otherwise, the P subarrays will be starved. As it is shown, fission requires irregular partitioning of the on-chip memory buffers and connection with the P subarrays. As such, there is a need to properly reorganize the architecture of the accelerator to realize fission for on-chip memory as well. This reorganization is necessary and needs to also be diligent. As this slide shows, fissioning the systolic array while keeping the original on-chip memory organization as the conventional systolic architectures will lead to severe starvation and an underutilization of the P subarrays, as only the bottom left subarrays has connectivity to the on-chip memory banks. In order to provide all the possible flexibilities with fission, in another hypothetical design point, all the subarrays could be connected to all the activation and output buffer memory banks with high radix crossbars. This design, although provides the required flexibility in the connectivity, but it would impose significant overheads. In a sense, these two hypothetical designs are the two extremes of a design range where one imposes minimum overhead with also providing minimum flexibility, while the other provides maximum flexibility with maximum overheads. To strike a right balance between the flexibility and the overhead of the design, we propose a middle ground design point called Fission Pod. Fission Pod interweaves compute and on-chip memory to provide balanced cooperation of them while minimizing the cost of fission. In this unit, a group of omnidirectional P subarrays are co-located and a partitioned memory substrate is shared amongst them. Now let's see how the architecture of this unit provides the aforementioned objectives while also considering the constraints. Each P subarray is coupled with a small segment of a SIMD vector unit to enable creating standalone and full-fledged logical accelerators. Based on the fission configuration, if a number of subarrays are stacked vertically, these SIMD vector units can be bypassed. To facilitate the omnidirectional flow of data across the configured logical accelerators, Fission Pod harbors a set of bidirectional ring buses that move the input activations and partial sums across various P subarrays in all directions. These buses can be also turned off if there is no communication between the adjacent P subarrays based on the target fission configuration. This intra and inter-omnidirectional flow of data paves the way to enrich the efficient possibilities. Additionally, the shared memory substrate in the fission pod is connected to the P subarrays via read and write crossbars to provide the flexibility required by various patterns of communication in fission scenarios and maximize the utilization of the P arrays and on-chip buffers. Moreover, since this memory substrate is shared amongst a group of subarrays, not all of them, the required flexibility in the communication pattern can be provided by using low-cost crossbars, minimizing the overhead of fission. Now let's look at the overall architecture. We integrate a collection of fission pods and expand the bidirectional ring buses across the whole design to increase the number of fission possibilities. Note that all the ring buses are pipelined to eliminate any critical path. We implemented and evaluated an instance of Planaria with 4 fission pods and 16 number of total subarrays. With this design, Planaria supports simultaneous execution of up to 16 DNNs and provides 65 fission scenarios in total. In a fission scenario, multiple fission pods can be potentially composed together or a logical accelerator can take a portion of a Fission pod while the other portion can be composed with other pods. As the second prerequisite for spatial multi-tenancy, we also define a task scheduling algorithm. To fully leverage dynamic architecture Fission while maximizing the throughput, fairness, and quality of service, the scheduler requires a set of characteristics. First, it needs to be aware of optimal Fission configurations for various layers of DNN to maximize the utilization and efficiency. Second, it needs to be quality of service aware to leverage the intrinsic slack time available in the task quality of service constraints during co-location to maximize throughput. Third, it needs to reallocate the tasks with minimized checkpointing overhead. To that end, at the compile time, we perform an exhaustive search to determine the optimal Fission configuration for each layer of target DNN with any number of subarrays within the range of 1 to 16, and create a set of configuration tables that capture the optimal Fission configuration for each layer, number of tiles for that layer, and the number of cycles per tile. These tables are consulted by the scheduler to predict the remaining time of each task with respect to its Fission configuration. During the runtime, the task scheduler monitors the progress of each dispatch task by keeping the information about the start time, the latest expected end time, and the current status in completion of the DNN task. Now let's look at the scheduling algorithm. The scheduler is invoked whenever a new task arrives or a task finishes. It then estimates the minimal resources with their optimal configuration for each task in the queue to ensure that all the tasks meet their quality of service. Then, if the total number of required resources is less than the total subarrays, the scheduler will co-locate all the tasks and allocate the minimal resources. After allocation of minimal resources, it incorporates a task scoring mechanism considering the task's priority and their remaining time to allocate the remaining resources with respect to the task scores. However, if all the tasks cannot be spatially co-located, the scheduler calculates scores for the tasks considering their priority, slack time, and minimal number of resources required to meet the quality of service. Then it sorts the tasks based on their scores from maximum to minimum and starts allocating the estimated resources until the resources finish. Only when the resource allocation for a task changes, the scheduler preempts that task and reallocates the resources. The scheduling events also happen at tile granularity to minimize the preemption overheads. We evaluated the proposed spatial multi-tenant design for inference as a service scenarios made up of randomly generated inference requests to 9 DNN models. We followed the MLPerf methodology for evaluation and also considered 3 workload scenarios with respect to the load of DNN models and 3 levels of soft, medium, and hard quality of service to well exercise the design. We compared our work to Premo, a very recent effort that considers temporal multi-tenancy. With the same frequency, number of compute resources, and on-chip memory storage, Planaria improves the throughput by 7.2x to 12.2x for workload scenario C as the most comprehensive workload that encompasses all DNN models. In terms of satisfaction rate in service level agreements, Planaria improves this metric by 15% to 45% across various quality of service constraints for workload C. In terms of fairness, Planaria provides 1.9x to 2.3x improvements. We also evaluate the benefits provided by dynamic architecture Fission and compared its performance against unconventional systolic array while executing the DNN models in isolation. On average, Planaria improves the speed up and energy reduction by 3.5x and 6.4x respectively. Moreover, dynamic architecture Fission provides significant improvements while executing the recent DNN models with depth-wise convolution. This unique capability enables much higher resource utilization while running this class of DNS. For more results, please refer to the full paper. To conclude, the community has rightfully focused so far on an arms race to maximize the performance and efficiency of the DNN accelerators. However, scant attentions have been paid to the utilization of these highly venerated accelerators. It is timely to address multi-tenancy as the third dimension towards enabling machine intelligence in our computing fabric in a cost-effective manner. We hope that this initial effort motivates the community to engage and expand the timely requirement of multi-tenancy for DNN accelerators.